Okay, so in the last session, we started the session on how you represent knowledge using logic, and we just saw the different types of logic that are available. So today we'll take up the simplest logic that is possible, which is the proposition logic. So here each statement or each sentence is a proposition. For example, if you say John is Mary's uncle or Bob's car is blue, um, I went to the cinema yesterday. So the entire sentence is a proposition. So you can't take part of the sentence and say it is a proposition. For example, can't say Bob's car or John's, Mary's uncle, etc. because that doesn't have any truth value. Okay, so when we talk about a proposition, the proposition is either true or it is false or maybe unknown, but it has a truth value. Okay, so when you say Bob's car, you can't assign a truth value to that. So we can say that a proposition is the complete sentence. And you have simple propositions, and these simple propositions can be combined together to make more complex propositions. So you have to use connectives for that. So two sentences can be combined together by using things like and, or, not, implies, or double implication or equivalent. So what you are doing here is using a connective to combine two sentences to make it into a single proposition. So what are these connectives? So when we say X and Y, we need to have a truth value for that also. So what would be the truth value of X and Y? So suppose X is true and Y is true, then X and Y will be true. What about X or Y? If X is true or Y is true, so if one of them is true, then X or Y will be true. And not X is true if X is false, and false if X is true. And X implies Y. If we assume X is true, then Y is true. That is, truth of X implies that Y is true. So X implies Y can also be written in this way. So we can say X implies Y is the same as saying not X or Y. Okay, so these two are equivalent to each other. And you have X double implication Y, which is true if both X and Y are true or X and Y are false. But if they have different truth values, then X double implication Y will be false. So these are the various ways in which sentences can be combined. So when we talk about language in knowledge representation language, we talk about two things. So one is the syntax and the other is the semantics of the language that you are using. So when you talk about syntax, it is the symbols which you are using, are the symbols that you are using following the rules of the logic or not. Okay. So symbols of propositional logic are true, false, and you have symbols like P or Q, A, B, whatever, and logical connectives between them and parenthesis, which means if you take a sentence and you put a parenthesis around that sentence, that is another proposition. So they are made by putting symbols together using the following rules. True and false are sentences by themselves. So you can have just a sentence which says it true. And proposition symbols such as P, Q is a sentence by itself. Wrapping parentheses around the sentence also yields a sentence, and it can be formed by combining simpler sentences with one of the 5 connectives that we spoke of. So if we look at the 5 connectives, not is the first connective, so that is the negation. So if you have a sentence A, the negation of that sentence A is where you use the not. And next is the and. So and is the conjunction. So when you say A and B, it's a conjunction of 2 propositions A and B. And each of the parts is known as a conjunct. Third one is the or connective. So if we take the or, it's called a disjunction. So we can say A or B, right? It's a disjunction of 2 disjuncts. So in this case, in this particular sentence, A and B is one of the disjuncts and C is the other disjunct. And then implies, implication. It's called an implication or a conditional. So you can say something like A and B implies not C, or A implies B, right? So it's something like if then rules, that is if, in this particular sentence you can say if A and B is true, then not C is true. So if you look at an implication sentence, it has 2 parts. You have the premise or the antecedent which comes before the arrow or the implication symbol here, and the conclusion or consequent. So here the conclusion or consequent is not C. So sometimes they use other similar symbols for it, right? And if and only if. So this biconditional is another way of talking about this biconditional is to say if and only if. So when you say this particular sentence, it means that A if and only if A, then not C, right? You can also write it like this, which is something like saying they are both equivalent. The left side and right side are equivalent to each other. So any logic can be represented in the form of the Backus-Naur form or the BNF as we call it, right? Even the English language you can represent as a BNF, and we will see that when we come to the natural language processing section. So in this case, this is your Backus-Naur form for propositional logic. So here we have a sentence to be equal to an atomic sentence or a complex sentence. Atomic sentence means what? It means true, false, P, Q, R, A, B, whatever symbols you want to use, right? You can put all of them here. And that those are the, so you'll be using true or you'll be using false. So that's why you put it in this way. And if you take a complex sentence, it consists of a sentence with parentheses, or if by using all the any of the connectives. So if you use any of the connectives, then you get a complex sentence. A sentence followed by a connective followed by another sentence. Or you can have combinations of these also, right? So then the operator precedence is put. So for example, in English, in math, in arithmetic, we have the operator precedence. So the brackets will come first, etc. The multiplication, and then the division, and then the addition, subtraction, etc. So this is your operator precedence that we have. So not has the highest precedence, then you have and, then you have or, implication and double implication. So this is the way of representing your propositional logic in the form of the Backus-Naur form. So when you're talking of a sentence which is there in propositional logic, it should follow all the rules that are set out here in this Backus-Naur form. If it does that, then we say that it's a well-formed formula, which means it is following all the syntax rules. So let us look at this order of precedence. So we said not comes first, and then or, then implication and double implication. So suppose we have a sentence like this, not P or Q and R implies S without any brackets at all. Okay, so if you are already given brackets, then that has the brackets will have the highest precedence. So here, since not has the highest precedence, it's going to be not P. Okay, so not P is going to be there. Next highest is and. So Q and R. So Q and R you can put within the brackets like this, and then the or, and then the implication. So the implication comes last. So if you take something like this, P and Q or R, so this will be P and Q in brackets or R, if you follow the order of precedence. And what is the semantics? So the semantics is the important thing, because it is the interpretation of those symbols that we write down. So we should be able to, it depends on what the computer interprets that proposition as. Okay, so you give some interpretation to those symbols and the constants and the connectives or whatever you are using. Okay. And the semantics, obviously we are talking about the output as being either true or false. So a proposition is either true or it is false. And a complex sentence has meaning which is derived from the paths. So a complex sentence will have simple sentences. For example, suppose I say A and B. So the truth value of A and B will depend on the truth value of A and the truth value of B. So if there is a complex sentence with two atomic sentences, okay, with connectives in between, some connective, then we can see what are all the interpretations it can have by using what is called the truth table. So let us see what this truth table is. So here we have taken two propositions P and Q. Okay, and if we take two propositions P and Q, there are four possible values. So you can have both to be equal to false. One can be false, the other can be true, or both can be true. So for different values of P and Q, we are finding the truth value of these various complex sentences, right? Not P, P and Q, P or Q, P implies Q, and P double implication Q. So if we take not P, obviously if P is false, not P is true. If P is true, then not P is false. Okay, so and if we take P and Q, we said that both P and Q should be true, only then P and Q will be true. So it's true only when both are true. And P or Q, one of them has to be true. So if we take P or Q, you find that in these three cases you get the truth value true, and in the first case it is false. And P implication Q is the same as saying not P or Q. So you are taking, this is not P or Q. So these two, if you take, these are the values you are going to get. And P double implication Q, like we said, if both are true or both are false, this will be true. In other cases, it is false. So in this way, for any sentence that you have, you can get the truth value of that complex sentence by looking at the truth value of the individual atomic sentences that you have in it. So suppose you have a truth value like this, and the truth value of the sentence is true for all the rows that you're talking about, then you call it you say that it is valid or it's a tautology. For example, if we take this particular sentence, which is a complex sentence made up of P and H. So P or H and not H implies P, right? So we take P and H and we do all these things. So for P and H different truth values, you find that this particular sentence that you have here, okay, has a truth value of T for all the four cases. So we can say that this is a tautology, or it's a valid sentence. Okay, so what are the rules of inference? So when we have a logic, you should be able to infer new sentences from the logic that you have. So how do you infer new sentences? So in other words, what you're trying to do is you're trying to entail a new sentence from what is already there. So the first rule is what is called the modus ponens. So suppose you have something which says A implies B, and you know that A is true, right? So if A is true, then you can infer alpha beta. So what happens is that this is the notation that we are going to use here, okay, when we are talking about rules of inference. So when the numerator is given, then you can infer the denominator. It's also called entailment. So you are entailing this beta from, if this is there in the, or it is given to you. And elimination A and B, you're inferring that alpha is true, right? So this says that from a conjunction, any of the conjuncts can be inferred, right? So when you say A and B is true, it means that A has to be true and B has to be true. So you are inferring you are entailing alpha when you have A and alpha and beta. And the third one is the biconditional. So biconditional A, biconditional B means you can entail that A implies B and B implies A. And the other way around, if A implies B and B implies A, then you can entail A double implication B, or alpha double implication beta. And finally you have the resolution. So this is a very important rule of inference which is used when you are trying to do theorem proving. So suppose you have alpha and beta and minus alpha, this not alpha and beta. So if you have two sentences like this where you have alpha here and you have not alpha here, then you can combine these two sentences to get a new sentence here. So what you are doing is this alpha and not alpha is being removed, and you are getting beta and gamma. So this is what you are inferring from these two sentences. So beta and gamma is being inferred from this sentence and this sentence together. So that is the resolution. So we make use of all these rules of inference when we are trying to carry out theorem proving. Okay, now suppose you have a knowledge base and you are using that knowledge base and you are entailing a particular conclusion. You are drawing some conclusion from that knowledge base. Now what happens is, suppose you add new sentences to that knowledge base. Can you draw the same conclusion? So when you are able to draw the same conclusion, then you say that it is monotonic. Your knowledge base is monotonic. So even though you are adding new sentences to it, the old entailments which were done still are true, right? But if this is not true, then you say that it is non-monotonic. Okay. So in other words, if knowledge base 1 entails alpha, then if you add on say knowledge base 2 to knowledge base 1 and make it into one knowledge base, if alpha is still entailed by this also, then you say that it is monotonic. So a monotonic knowledge base is much easier to deal with, right? If it is non-monotonic, it becomes difficult to deal with such a knowledge base. Okay, so these are the laws that are followed by propositional logic. So if you negate P and you negate it again, you again get P. So that's called double negation. And P or Q is the same as saying not P implies Q. Then you have contrapositive law, which says when you say P implies Q, it's the same as saying not Q implies not P. And De Morgan's law is a very important law. So here when you have P or Q and you are taking note of that, then you can take this negation inside, and when you take the negation inside, the OR will become a AND. So you will get not P and not Q. Similarly, not of P and Q, you can do the same thing. You take the negation inside, but the AND will become a OR basically. Then we have the same type of laws that we have in arithmetic, etc., the commutative law. So when you say P and Q, it's the same as Q and P. And P or Q is the same as Q or P. Then you have the associative law, again similar to what we have in algebra and arithmetic. So when you have P and Q and OR, it's equivalent to saying P and Q and OR. Similarly, P or Q or R is equivalent to saying P or Q or R. Okay, that's the associative law. Then you have the distributive law where you use both and or. So if we have P and Q, P or Q and R, this will be P or Q and P or R. And similarly, P and Q or R will be P and Q or P and R. So this is the distributive law. So you will be using all these laws when you are trying to simplify sentences and bring it into a certain form to carry out inference. Okay, so these are the same equivalents we talked about before. Commutativity of and commutativity of or, associativity, and then double negation, contraposition, implication, elimination. So when you say A implies B, it's alpha implies beta, it's equivalent to saying not alpha and or beta. Okay, so this implication elimination also is used heavily when you are trying to reduce or to simplify your knowledge base. Biconditional elimination. So if you want to eliminate the biconditional here, alpha double implication beta, you can say alpha implies beta and beta implies alpha. And de Morgan's theorem we saw, and distributivity. So these are the same as what we saw in the earlier slide. Okay, so how do we carry out resolution? So, or when we get a set of clauses, okay, and then you are given a clause which you need to prove, is this true? What do you do? So, you use what is called resolution refutation. So, all the sentences that you have, that is the well-formed formulas, all of them are combined in a knowledge base. So when you say delta, you mean one knowledge base. So you are going to convert it into a conjunctive set of clauses. So it means you have one clause and then you have another clause, all of them together form your knowledge base. Then you convert the negation of the what you want to prove. Okay, so what you want to prove is W. So you take negation of W and add it on to this knowledge base. Okay, and you combine the clauses to form a single set. Then you apply resolution to the clauses. So we saw what resolution is, right? If one sentence has say alpha and the other sentence has not alpha, then you can combine them together by removing these two. So we'll see how we do this. So what happens is, if you keep on applying resolution and you come to a point where there are no more resolvents that can be added, or you get the empty clause, this means that the W can be entailed by your knowledge base. If the knowledge base cannot entail W, then you will not get the empty clause. So first what we do is to convert the sentence to conjunctive normal form. So when we say conjunctive normal form, we mean that each of the clauses will have only disjunction in it. Okay. So for example, when you say P implies Q and you get not P or Q, okay, this is one clause and you may get a number of such clauses. So the first step that you need to do is to eliminate the implication. So how do you eliminate the implication? P implies Q is equivalent to not P or Q, and then you reduce the scope of the negation. So if you have negation of P and Q, it's equal to not P or not Q. That's the De Morgan's theorem. And then you convert to CNF by using associative and distributive laws. So let us take this example over here. So here we have these are the WFFs which were given, that is the well-formed formulas. So here we take each sentence and we need to bring it down to its simplest form. So here you have a double negation, so you will get Q. So you will get Q and Z. The second one is not W. The third one you need to remove this implication, which means you will get not W and Q and not P. So suppose we open out the brackets and simplify this, you are going to get, so you have the De Morgan's rule being used here. So you will get W because double negation, or not Q or not P. So similarly here also you just take not of this or S and simplify that. Similarly same thing you do here also, you are going to simplify this. Here also you are going to simplify it. And then suppose we want to show S or R. Okay, so what do? You take not of S or R. So if you take not of S or R, you will get not S and not R. So what you do is, when you convert it to conjunctive normal form, you are going to get these sentences here. So not S and not R is taken as two separate sentences. So when you say conjunctive normal form, it means that your knowledge base will consist of 1 and 2 and 3 and 4, etc. So when you say not S and not R, you take them separately. Okay, so two different clauses. So this would be your conjunctive normal form. So what you have to do with this is, you have to start using resolution. So suppose I choose two sentences, say 1 and 5. I can combine 1 and 5 because this has Q and this has not Q. So you can combine them to get a new sentence or new inference. And you can keep doing that. And once you do that, if you come to finally you come to a nil clause, then you can say that you can stop at that point in time. Okay, so let's see here. So here if we take not W and W, etc., you're going to get this, and if we resolve this with Q, you will get not P, and if we resolve this with this, you will get etc. And we are coming out with the nil finally. So since we are coming out with the nil, it means that this S or R is proven, it's true. Given this knowledge base, you can entail S or R from that. So that's what you're basically trying to do here. So this is the propositional logic. The problem with propositional logic is that it is too simple. You can't represent everything using propositional logic. But the reason why we study propositional logic is because we want to study the simpler thing and then move on to the more complicated logics that we are looking at. So, what we generally use is what is called the predicate logic or the first order logic. So, we can see here that there may be too many propositions to handle. If you take a real world situation and suppose you have the same variable with different subscripts, okay, and for each of them you have to keep writing new propositions. So it becomes really large, the number of propositions. Second is that time dependent things require every time step to be taken as a new proposition. Okay, so again you have the same problem, too many propositions will be there. And what happens is that we have a very simple thing like the entire sentence is represented as one proposition. But in first order logic or the predicate logic we are going to talk about, you have objects, you have relations, functions and quantifiers. Okay, and using all these, it's possible that you can dispose of a lot of propositions in the propositional logic by using just one sentence, right? It's something like saying, okay, I have a variable x and x can take different values. So because of that, you find that just one sentence is enough to displace or dispose of so many propositions. So we'll stop here at this level, and in the next session we'll start with the predicate logic.